In Lecture 6, we will start talking about impulse and momentum. Impulse and momentum equations are also derived from the Newton's formula F equals ma. The summation of forces acting on the particle results in the acceleration of that particle. If we integrate this with respect to time, then we receive the impulse and momentum equations. The first part we're going to discuss is on linear impulse and linear momentum. In order to start our discussions, first off, we define the linear momentum of a particle. The letter we're going to use for the linear momentum is G. You will see in some books it is used as P as well, P to define the linear momentum. But in this course, we will use G, the capital G, to define linear momentum. And linear momentum is a vector, and it is equal to mass times the velocity vector. Therefore, its units is mass units, kilograms, and then velocity, meters per second. Or as Newton's is kilograms meters per second square, now the linear momentum's unit is Newton seconds. We can define this F equals ma formula in another way as well, which is the differentiation of velocity vector with respect to time. So v dot is actually equal to a, acceleration. And then, as we consider this m as a constant, then we can define this as the derivation of the linear momentum. This was defined as g, right? And then derivation of the linear momentum with respect to time, that is equal to the time rate of change of the linear momentum. So g dot is the time rate of change of the linear momentum. So we can let's say define the Newton's equation as summation of forces acting on a particle results in the time rate of change of the linear momentum, which is g dot. Now let's take a look at a sample drawing for this. There is a path of the particle. As that particle moves along that path, it is at a location at t1 seconds, and it's at another location at t2 seconds. And the velocity that it has at t1 is different from the velocity that it has in t2. The difference is in terms of the magnitude and also in terms of the direction. Now, what causes this change is the summation of forces, the net forces, in other words, acting on this particle throughout this path from t1 seconds to t2 seconds. So, like I said, if we integrate this equation, F equals to the time rate of change of the linear momentum equation with respect to time from t1 to t2, as a result of that, we receive that the integration of net forces acting on a particle from t1 to t2 seconds results in the change of the linear momentum from g1 to g2. And by definition, we call this integration as the impulse of the force. Impulse of the force from t1 to t2 seconds results in the change of the linear momentum delta g. Again, this is a vector equation. Remember that in the vector equations that we use for the Newton's equation, we were able to get two scalar equations for the planar motion of a particle. For the three-dimensional motion of a particle, we would get three equations out of it, but in plane we got two equations. Similar to that, this is a vector equation, and then we will get two independent scalar equations on plane. For a three-dimensional case, that will be three independent scalar equations. So force times time is defined as the impulse of the force. G1 is defined as the linear momentum at T1, G2 is the linear momentum at T2, and the first thing we need to do for such an investigation of impulse momentum is to draw the free body diagram and observe the forces acting on the particle. Now, if we are to talk about conservation of linear momentum, that means for an interval of time, if the net forces acting on the particle is zero for that interval, in that interval, the linear momentum did not change. So whatever the linear momentum of the particle was, it is conserved. And then you can approach to this information in a resolved motion case, which means that this is a vector equation, but then in plane we get two equations, in space we get three equations, three scalar independent equations. So among these equations, if in one of the axes, in one of the directions, the summation of forces in that direction through that interval of time is equal to zero, then although the forces in the other directions are not equal to zero, the linear momentum in that specific axis where the forces, net forces, are equal to zero in that interval of time will remain the same. So the linear momentum along that axis will be conserved, and delta Gx being equal to zero tells us that the linear momentum along the x direction has been conserved. Now, again, basing our discussions on Newton's laws, action and reaction, if we have two particles, A and B, which interact, a physical interaction, so they collide during an interval of time, and this is an impact case, in this case, if there's a F force acting on particle A, so let me just draw a particle A here, there is, because of the impact, there is an F force acting on this particle, and these are separate free body diagrams. This is the free body diagram for A, and then free body diagram for B. This small caps, so let me just change this. This is not A, small caps A particle. This is the small caps B particle. In that case, there is an equal amount of force in the opposite direction. Equal amount of force. Oops. This, okay, equal amount of force in the opposite direction. So if you call this positive, then the other one is negative in the sense of the direction. Okay? So if the interaction forces are F, and let's say that we choose this as the positive direction. So in the example that we have is the opposite, so let me just be consistent with that. In the other direction, let's say this is the positive direction. In that case, positive F force is applied on the particle A, and it results in the change of the linear momentum of particle A, and then a negative F, the same magnitude but different direction force, is applied on particle B, and as a result of that there is the change of the linear momentum of B. But if we add them up, as you can see, this is positive F, this is negative F, the results should be equal to zero. That means the total change in the linear momentum of this system of particles, these are two particles now, is equal to zero. So the total change in the linear momentum of particle A plus the change in the linear momentum of particle B should be equal to zero. And this is going to be called the conservation of the momentum of a system. In this case, the system is composed of these two particles, A and B. And in this case, because of these interaction forces, the linear momentum of the system stays the same because there's no other external forces, only internal forces. So you can deduce that if there exists only internal forces in a system of particles, then the linear momentum of the system will not change. Okay. That being said, we have similar type of information here, so I'm not going to talk about it. That being said, we're going to take a look at the example in the next video.